Hello students, good morning, good evening and good night depending on in which time we are going to observe this video. Welcome to this lecture number 11 on state of matters. Before discussing the relevant topic in this lecture, first let us solve one very important numerical. This numerical relates to our previous lecture. In the lecture number 10, we have discussed about the liquefaction of the gases, right? Now, in this relation that we have studied and we have understand the critical temperature. So, one question is numerical is given that you have to arrange these gases in order of increasing their critical temperature. In order of increasing their critical temperature, that they are given, the van der Waals constants are given. That is, A is van der Waals constant, one of the van der Waals constant, and B is other van der Waals constant. Your gas is given A, B, C, D. Now you have to arrange which of the highest critical temperature and which of the lowest critical temperature. For that, you should know the relationship between the critical temperature and the van der Waals equation. What is that? That was discussed in the lecture number 10. If you have not watched this lecture, you must watch this. So, what is the relationship? Relationship is this 3A by RB. This is the relationship between the critical temperature and with the van der Waals constant. Now what we will do, we will make a constant here and you can see that is a liter atmosphere. That means the R will be given the 0.082. So here you can see the constant will be, because this will be all the constant. So it will be 3.60 into A by B. After that, we will calculate the critical temperature. And what will be the critical temperature? Let us understand. You can calculate yourself. And so if we calculate the critical temperature, we will get for the gas A, it is 534 Kelvin. Gas B, it will be 962 Kelvin. And gas C, it will be 634, and gas D, it will be this. So we can arrange the critical temperature in the decreasing order. You have to arrange it decreasing order. So this will be what will be the right answer? The right answer will be D, having the highest critical temperature, followed by B, and followed by C, and followed by A. So this will be the right answer. D, B, C, and. Okay. So in this lecture we are going to discuss another very important thing, that is the Joule-Thomson effect. So let us write what is Joule-Thomson effect, right? The Joule-Thomson effect is basically, you can define this when a real gas is adiabatically expanded to a region of lower pressure, through a fine hole or the porous plug. it This is the Joule-Thomson effect. When a real gas is adiabatically expanded to a region of lower pressure through a fine hole or porous plug, it accompanies with the cooling effect. But this cooling effect cannot be observed by the hydrogen and helium. Instead, the cooling effect you will find there is a warming effect to the gases. The gas will be heated after this adiabatically expansion of this real gas. So now answer to this, why this is happening. First let us understand. This is happening because of the fact when we expand the gas through a very small hole, there will be the work done by the gas molecules. When this work is done, at that time there will be the loss of the internal energy of the gas, and due to this loss of the internal energy, the temperature also reduces. That this phenomena is basically due to the work done by the gas on expanding, and that is creating the loss of the internal energy of the gas, and this is going to affect the internal energy of the gas, and the internal energy of the gas has been reduced, and it will ultimately affect the temperature of the gas. So there is you can see the cooling effect, but you cannot observe this Joule-Thomson effect for the ideal gases, because in the ideal gases there is no attractive force between the molecules, but in the real gases there is an attractive force between the molecules. So you can always observe the Joule-Thomson effect for the real gases. Now question arises, how do we quantify this Joule-Thomson effect? For that there is one parameter has been fixed, that is Joule-Thomson coefficient. Joule-Thomson coefficient is represented by mu, and this has been denoted by dt by dp, whereas the enthalpy, when expansion is going adiabatically, at that time there will be no enthalpy change, and that is why the H has been kept here, and this signifies this process is isothalpic. This process is isothalpic. There is no enthalpy change in this process. Enthalpy remains constant. There are three types of things you observe. When the Joule-Thomson effect, mu is positive, at that time you will find the cooling effect. Right? So at that time what you will find, dt will be negative and also dp will be negative. Both the pressure and the temperature, they will be fall. They will fall in the pressure and the temperature. But when mu is negative, mu is negative, at that time you will find the heating effect. So at that time what is going to happen, dt will be positive, but dP will be negative. So ultimately this will be have the positive effect. But when mu, number 3 case, when Joule-Thomson coefficient is mu is equal to 0, at that time what we find? No heating effect, no heating or cooling effect. So you understand the Joule-Thomson effect is basically, that is the when we expand the real gas adiabatically, and at that time through in a region where there is a lower pressure zone, at that time it will accompany with the cooling of the gases. But this effect will not observe for the ideal gases. This effect will not observe for the hydrogen and helium also. In hydrogen helium, if we carry out this adiabatically expansion of the gases, we will find there is a OR. Why it is so? Now let us understand. Understand why the hydrogen and helium is not going to respond to the Joule-Thomson effect, that is the cooling effect. Let us understand first the inversion temperature. Inversion temperature. What is inversion temperature? It is a temperature, we can write it. It is a temperature in which there is no heating or cooling effect. So at this temperature the mu will be 0. But below this inversion temperature, you can write again, below this temperature, there will be the cooling effect. And above this temperature, there will be heating effect. So below this temperature there is cooling effect. At that time the mu will be positive, Joule-Thomson coefficient will be positive, and below this will be negative. The hydrogen and helium have the very low inversion temperature. Hydrogen having the inversion temperature Ti is equal to 80 degrees Celsius, whereas helium Ti is equal to minus 240 degrees Celsius. So you can understand it will not going to show the cooling effect as per the Joule-Thomson's definitions. It will not able to show at the normal temperature. If you want to, it will show the cooling effect that we are talking about only when the temperature of the gas has been reduced below this inversion temperature. When temperature of the gas will be reduced below the inversion temperature. At that time, what will going to happen? There will be the sufficient intermolecular force of attraction will be there. The molecule will have the less thermal energy, and it do not have any speed at all. At that time, what is going to happen? There will be intermolecular force of attraction. So when there is an intermolecular force of attraction, then we have to do some work, and with this effect the internal energy of the gas will be reduced and it will show the cooling effect. So that is the main thing. When the inversion temperature will be very low, you will not observe this Joule-Thomson effect, that is the cooling effect on adiabatically expansion of the gas. So what is observed in case of hydrogen and helium also. Okay, so we understand the Joule-Thomson effect, how in case of hydrogen and helium we are not able to see the Joule-Thomson effect, right? Now we can correlate this Joule-Thomson temperature, that is the inversion temperature Ti with the constant, with the van der Waals constant, and it is 2a plus Rb. It is 2a plus Rb. The A and B is the van der Waals constant. So if we compare with the 2b, that is the Boyle's temperature. Boyle's temperature is what? That is A by Rb, and critical temperature we know that is 8 A by 27 R. So inversion temperature we can say it will be much more higher as compared to this temperature. Okay, so that is all for today's lecture. In this lecture we have discussed about the very important effect, that is the Joule-Thomson effect. How the in the Joule-Thomson effect there is a cooling effect for some gases, or there is no cooling effect for the other gases like hydrogen and helium. That also discussed in detail. Up to this we have covered total 11 lectures in the state of matter chapters, and hope you have go through all the lectures, and it will be helpful to you in your exams, in your concepts, clearing the concept. And in the lectures what we have done so far, in the lecture number 1 you can understand we have discussed about the very initial, very introductory things in the state of matters. That is why there is a different state of matters, that we have understand from this lecture, that it is the balancing of the two forces, that is the intermolecular attractive forces and the thermal energies, that is going to impact and attributed to the different state of matters. In the second lecture we have discussed about the Boyle's law and the Joule's law. Third lecture we have discussed Amonton's law and Avogadro's law. Fourth lecture we have discussed about the ideal gas law. Fifth lecture we have discussed about the Dalton law of partial pressure. Sixth lecture we have discussed about the Graham's law of diffusions. Seventh lecture we have discussed about other topics, other related topics, that is the kinetic molecular theories. Eighth lecture we have discussed about mean free path, that we have already discussed. Ninth lecture that we have discussed about the van der Waals equations. 10th lecture we have discussed about the liquefaction of the gases, and this lecture we have discussed the very important thing, that is Joule-Thomson effect. Hope you should go to the YouTube channel and you can type the Science with Mukherjee sir, and you go to the playlist and you will find all the lectures, and you must visit this lecture and you must report to you. Thank you very much for watching. Thank you.